Hi everyone, our project is bus schedule problem. In the part 1, I will give a brief introduction for our problem and the math form for it. To introduce our problem, first, I need to generate a graph G corresponding to the problem, and then use six sets to describe it: set of chips, set of stations, set of field stations, set of ports, set of chip chains, and all the locations in this graph G is V. One of the important sets is chip chain. This is a chip needs to start from the port to a certain station, then go through one or several chips, and finally return to the port. This is one of chip chain. This is the data used in our project. Bus cost is fixed, and other consumption is related to distance traveled. We use two variables in our project. One is XP. The optimal solution contains chip chain P. XP is 1. If the optimal solution does not contain chip chain P, XP is 0. PIP. If the chip I is contained in the chip chain P, BIP is 1. Otherwise, it is 0. This is two chip chain. If the optimal solution contains one of it, XP is 1. Otherwise, it is 0. The objective for our project is to minimize cost. To minimize our cost is the bus cost for each flexible chip chain plus cost for each flexible chip chains. Because one flexible chip chain needs a bus. There are some constraints for our project. Each chip occurs once. A chip can go to next chip with K fields. Each chip chain has enough field. These two constraints are mutually inclusive, and we only need one function in the code. In order to reflect the capacity of field and the per case of charging in the mathematical formula, we have written about the constraint to the chip chain. Each chip chain has enough time. The chip chain means capacity of the depot. Each chip chain starts from the port and finally back to the depot. We need to make the conservation of flow.
In part 2, we talk about the code and random data. For random data, we generated 100 locations randomly, and we allocate 100 trips and their time sequences to these locations. For example, the trip I's earlier starting time would always be earlier than the trip I plus 1 starting time, and we also save the fuel and time cost into the list so that can make the calculation faster. And we made the list below. For example, in the second line, it's talk about the fuel and time cost from trip A's endpoint to the depot D. We made a huge suppose here. We suppose that bus can refuel in depot after they finishing all the work, which is also means that a bus cannot go to fuel station if there is no trips left. Now it's about the generation approach. We made a data set called can reach. which meets the time constraint and fuel constraint. For time constraint, a bus needs to catch up the next trip's starting time. And for the fuel constraint, a bus needs to have enough fuel to go on the next trip. And also it should have enough fuel to go to the nearest fuel station after it finished the nearest trip. We call this can-fuel decomposition function. We import feasible trip list, current trip, current fuel, and output the candidate trip and the fuel station if the trip can be done only by visiting a fuel station. And the last value is the fuel after we do this trip. We use this as a fuel condition to calculate the next move. At first, the random function operates 300 seconds for 100 trips because we just involve a very general constraints. Then we make some constraints to eliminate a lot of schedules, which also in line with reality, such as we limit a schedule's max trips. What's importantly is that we filter the trip list just as what the successor set did in the course. So the can-fuel decomposition function can do less iteration. So at first, we improve the 300 seconds operating time to only about 75 seconds execution time, which is also slow, but it's a huge improve. And we plan to involve the branch and price function in the future. We haven't finished yet, but theoretically, we generate columns with trip I if its reduced cost is less than the current reduced cost with trip I. We stop until the reduced cost is equal to 0, because when the problem would become feasible, the reduced cost, the gap would be 0, would be equal to 0, or very, very close to 0. But the function now would get a relatively low but not optimal solution. There is something wrong with here. And we also found the final solution would have a different cost and fuel condition with the previous function. Where we generating all possible schedules at first, we deduced something is going wrong during the iteration. So basically my idea was that to revise the cost function so that we can calculate the cost by using only the trips rather than the fuel conditions. Okay.
Hi, in part 3, I will introduce the real-world problem for the bus schedule. But first, I will introduce the heuristic algorithm in our project. In our project, we make a few assumptions for the heuristic algorithm. First, each depot has limited vehicles, and then we should always make sure it has enough fuel to return to a depot after assigned a trip. So the algorithm has 3 steps. First, we should assign a trip to a vehicle from a depot which has the minimum cost. And then we should determine the feasible schedules for another trip and always find the minimum cost and have assigned the trip to a vehicle. We can use the can schedule function in the code to determine whether a vehicle needs to refuel or this is the first trip for a vehicle. So if this is the first trip, we should pay the bus cost. And the third step is to continue assign trips until all the trips are assigned. So this is the heuristic solution based on the random data. As you can see in the results, this is the first bus in the first vehicle, in the first depot, and this is the bus schedule. And after he was assigned 4 trips, he needs to go to the fuel station 2 and finally returns to the depot 2. And this represents the schedule cost, and this is the remain fuel when the bus came back to the depot. And as you can see, the time cost is very, very small. So when we compare the heuristic algorithm with the column generation, we can always see the heuristic algorithm can find the suboptimal results, but with a way much faster speed. This is the table that we fixed the number of depots and the number of stations and some other parameters and only changed the number of trips in the problem. And you can see the column generation time cost increased rapidly and the heuristic algorithm are always so fast. Then we came to the real world problem. So we get the data from the Xi'an, which is a city in China, and we have used the map API to find the real distance between two trips and the two stations and the real time cost. So this is the visualization for all the stations and the routes in the bus data. And as you can see, the red triangle represents the fuel station, and the yellow squares represents the depots. And also, this station and the depot position is based on the real map. We have some pre-settings, and those settings parameters are also based in the real world. So basically, these are money, right? So the fuel price for driving 100 kilometers in China is almost $24. So we just set the bus cost for daily salary for the driver is $24, and the max tour is 10 kilometers, and the fuel capacity is 20 kilometers. There are some things we can do in the following weeks. First, we need to reduce the time cost. And the second, in order to reduce the time cost, we can try the Gradient price. And then we can get an optimal integer solution by solving the sub problem. And thirdly, we can make depot able to be refueled so that we can reuse those data those buses that early returns to the depot. Thank you for watching.